Okay, page 5. We are doing an exponential graph first. So I want to identify the shifting, and I also want to identify the parent function, because these do not work off of movement charts. These work off of actual coordinates. So let's see, -5 tells me this is going to move to the right 5, and then -4 is down 4. We'll keep that in mind. Okay, so our exponential graph is going to work off of 3 to the x. So we'll put our exponents in the x column. And just work off of 3 to the x. So a negative power is going to square it and flip it. We got 1/9. So this is just going to flip, so 1/3. First power, or 0 power is 1. First power is 3. Squaring is 9. So this is the base table for 3 to the x power. But the shifting means I need to go right 5, so I need to increase the x's by 5. And I need to decrease the y's by 4. And that will move us to the correct coordinates. So -2 plus 5 is +3. -1 plus 5 is +4. 0 plus 5, 1 plus 5, 2 plus 5. And then, starting with these, 1/9 minus 4 is -3 8/9. Decimals are fine if you want. 1/3 minus 4 is -3 2/3. 1 minus 4, 3 minus 4, 9 minus 4. Alright, now I can go over here. Normally an asymptote would occur at 0 for exponentials, and it's horizontal, but because of the down 4, I actually do want my horizontal asymptote to drop down by 4. So straight across -4. Now I plot my points. So I move to the right 3, and then down 3 and 8/9, so pretty close to this -4 asymptote. Move to the right 4, and down 3 2/3. 3 2/3. It's a little bit higher than 3 8/9. Okay, to the right 5, down to -3. To the right 6 and down 1. And to the right 7 and up 5. And it does make a curve, as it's supposed to. So connect these points with a curve, and arrows at both ends. Okay, domain. So there's a left arrow and there's a right arrow. Also, algebraically speaking, there's never a limitation on what I can use for an exponent. So that's another reason why it's an unlimited domain. For the range, there is a bottom to this graph. It occurs at -4. And there is not a top. It just goes up and up and up. So -4 to infinity. For end behavior, as we move to the right, we are going up and off the grid. As we move to the left, we're not going down and off the grid, we are going to this -4 asymptote. And when we describe a horizontal asymptote, it is a y equals line. So y equals -4. Alright, 37 is a log graph, so we'll do basically the opposite of everything. This +1 tells me it's left 1, and +3 tells me it's up 3. I look at the subscript to get my base. But in my table, for a log, I switch which side is which. So my exponents are going to actually go in the y column. I use 2 to the x, and I write the results in the x column. So it's the inverse table of the exponential version. Come over here, we have left 1, so that means I need to decrease my x's. We're up 3, so that means I need to increase my y's. Make some new coordinates, and we'll be able to graph it. So decreasing, so 1/4 minus 1 is -3/4. 1/2 minus 1 is -1/2. You get 0, 2 minus 1 is 1, 4 minus 1 is 3. Over here I'm adding 3, so -2 plus 3 is 1, and then 2, and then 3, 4, and 5. So those are the points I want to plot. Also on a log graph, the asymptote becomes vertical. Defaults to 0, but we have shifted this to the left 1 unit. So we're moving over to the left 1 unit. A vertical line cannot go up or down, it can only go left or right. And the one before it the horizontal line could not go left or right, it can only go up or down. So we don't always shift these things, we just shift them if we have the right type of shifting. Okay, coordinates, negative 3/4, so a little before the line, and positive 1. Negative 1/2 and positive 2. 0 and 3. 1 and 4. 3 and 5. And we get our curve up and away. All right, now if this base subscript was a fraction, then we would do all the same things, except that when we have negative powers on fractions, they become whole numbers. So these would actually go downward, and it would make the curve go like this. So that's the only difference, but this graph is right for a whole number base. Okay, domain is restricted because of the asymptote. I'm restricting it from -1 to infinity. Range, I have a down arrow, I have an up arrow, so we're just going to go with an infinite range. For end behavior, I need to know what the x's are doing. So I look at the y's. This is describing an up arrow. The up arrow is moving to the right. The down arrow is moving to the left, but only until it gets to -1. And we describe a vertical asymptote as x equals. That one's done. Okay, some equations to solve. So if we have the same base, we can simply cross out the bases and write an equation with the exponents. So subtract x, subtract 5. There's never a restriction with exponents, so we don't have to bother checking that. What you also need to be aware of, though, is you could just as easily have had a 5 and a 25, or even a 25 and a 125. So a lot of times these need to be converted before they can be crossed out. So just be aware of that. That comes up here, actually. So I have a 4 and a 1/16. Can't cross those out because they're not the same. But there is a way to rewrite the right side as a 4. I just need an exponent on that 4 so that it equals 1/16. So this would need to be a -2 in order for this parentheses to equal 1/16, because it would have to flip and square. Alright, so if I multiply those exponents now, I can cross off the 4's. I'd have -2x plus 6. Here I have x plus 2. So if I add the 2x, I get 3x. Subtract the 2, I get 4. So x is 4/3. Alright, next one's a log equation. And I have logs on both sides, so those logs can go. 5x plus 9 equals 6x. Subtract the 5x. And that's it. X equals 9. With log equations, remember we do need to check them, because logs can't be negative inputs. So if I have a 9 here, I'm good. If I have a 9 here, I'm also good. They both equal positive numbers. All right, next page, page 6. More log equations. All right, 41, I have logs on both sides. However, the one on the right side is not condensed yet. This 2 needs to become an exponent. The minus indicates that I need to make a fraction out of these log inputs. So it's a single log at this point. And I'm going to have 36 from the 6 squared divided by 4. So log 3 of 9. All right, over here I have log 3 of 2x minus 5. So the logs get crossed out now that I'm down to 1 on each side. All right, so 2x minus 5 equals 9. Add the 5, 2x equals 14, and x equals 7. Just go check it, and the only place there's an x is here, and it's a positive number, so we're okay. X equals 7. Okay, 42 has logs on one side only, so I need to condense them, but then I'm not going to be able to cross them out. I'm going to have to use an exponential conversion. So it's a plus sign, which tells me I need to multiply these. So if I just distribute this x back into the first one, I'll have a log, and I'll have an x squared minus 3x equals 1. That's the most common mistake there. People try to condense it and then they forget the log. But it's still a log at that point, which matters because now there's only one log, can't cross it out. Base is unwritten, therefore it's 10. Exponents across the equal sign, and we can solve now. Subtract the 10 over, and it is factorable. X minus 5, x plus 2. Solving chart would give me 5 and negative 2. Let's go back and check. Negative 2 is not going to work. Not in either location. 5 is good here, 5 is good here, so just x equals 5. Okay, number 43. And again, just a single log, so the base is 2, power 6. And it equals x minus 4. This is 64, so if I add 4, x equals 68. And we're okay there. Natural logs work the same as logs. So let's see what we want to do with this. I think we want to look at a conversion and then a condensing. Okay, so this is x plus 7 cubed. And this is still 8. And this 6 comes up, and I have ln of 2 to the 6th. Okay, so if I make a fraction here, no, not a fraction, if I multiply here, what I would have is a natural log of 8 times x plus 7 cubed. And over here, 2 to the 6 is 64. Okay, well, one natural log on each side, let's cross them out. So I have 8 times x plus 7 cubed equals 64. I don't really feel like multiplying out this binomial. I mean, I could expand it, but I don't really want to do that. I'm just going to divide 8. So I have x plus 7 cubed equals 8, and now I could just cube root. Right? So if I cube root both sides, cube root takes away cube. Cube root this side, I just get 2. So I have x plus 7 equals 2. Subtract the 7. X is negative 5. Go back and check it. Negative 5 does not create a negative log, so we're good. All right, let's keep on going here. Number 45, I have a single log. I cannot cross it out. So I need to look for a base. And the base on this is unwritten, but we know that a natural log has base e. And then the exponents across the equal sign, so e to the 6th, 4x minus 7. E to the 6th is approximately 403.43. And then add 7, I have 410.43. And just dividing by 4, I get 102.61. That's all done on a calculator. E to the 6 on a calculator, add the 7, divide the 4. All right, no worries with making a negative log. Okay, now I'm into exponential equations, which means I either need to solve them with common bases or I need to be using a log. No way I can convert 18 into a 3 though, so I am going to need a log. And the way we do that is we look at the base where the exponent resides and make that my subscript of my log. The exponent goes across the equal sign from a log, and then we fill in the 18. Okay, so you can use your Math Alpha math feature on this and get your result. You should have x equals 2.63. Just a reminder though, if you're using a calculator that does not have that feature, you can always put the subscript on the bottom and do a log fraction. That will also give you 2.63. So whichever way you need to do it based on the calculator you're using. Okay, 2 more here. Again, no way to get a common base, so let's do a log. Subscript 15, 3x minus 5 goes across, 87 comes in. If you solve this log, you get approximately 1.65. Add the 5, and divide the 3. And a lot of that, you can do that whole thing on your calculator if you want to. You just do the log and then while that number's on the screen, add the 5, and then while that number's on the screen, divide the 3. You can get there that way too. You never have to bother looking in an exponential because an exponent can be anything. It's an unlimited domain, so we don't have to worry about whether it makes a negative or not. Okay, dividing 5 here. And the reason I have to do that, you always need your base to be isolated. So I have to get the e by itself. So now I have e to the x minus 3. And e is solved with a natural log. Exponent goes across, and the 7 comes in. So solve natural log 7, you get 1.95 approximately. If I add the 3, I'm at 4.95. And we're good. Okay, that'll do it for page 6.